So right now I want to discuss section 2.4, which we're going to call sequences, series, and recursion. Suggested exercises are 3, 13, and 17. The main things we're going to talk about are sequences, series, and recursive sequences. We'll also talk about summation notation. That's with the Greek letter sigma. So for our purposes, a sequence is an ordered list. Usually of numbers. So you can have a sequence of anything, but it's typically going to be a list of numbers. We write, and so this is a little maybe confusing, so I'm going to write in curly braces a sub n, and then I'll write n goes from 1 up to infinity. Now what this means, this notation here means that each element is called a and it's indexed with an n, and n is starting at 1 and it's going up to infinity. Now sometimes we'll have, this n could start at 0, or n could go from negative infinity to infinity, or n could go from 1 to some constant, but this is typically how we write things. And this is just to say a1, a2, ... on and on. Now the difference between this and a common set is it's ordered. So with a set, we don't care about the order. With a sequence, we care about the order. So let's do an example. Let a sub n equal 1 over n plus 2. Then we have, a sub 1 is going to be 1 over 1 plus 2, which is 1/3. A sub 2 is 1 over 2 plus 2, which is 1/4, etc. And we could presumably list off any element from that sequence just by using this formula. Now this formula is what we call a closed form because it uses the value of n explicitly in the definition. Okay. That might not make so much sense until we contrast it with a recursive definition. So I'll say a recursive definition of a sequence is defined by giving some terms explicitly, put some term or terms explicitly, and defining the others using previously defined terms. And so let me give you an example of this, and then we can contrast it with what I called the closed form. This is what I called closed form. So the recursive definition is going to be something like, let's let a sub n be, well, let's define a term first. Let's let a sub 1 equal 1, and then we'll let a sub n equal 2 times a sub n minus 1. So then we can figure this goes 1, well 2 times 1 is 2, 2 times 2 is 4, 2 times 4 is 8, etc. Now you could say, well, why not just define this as a sub n is defined as 2 to the n, or in this case 2 to the n minus 1 if we're starting at 1, however you want to think of it. Some people like to start sequences at 0. I think in the notes I start with a0 instead of a1. It really doesn't matter. This would be the closed form. So the closed form version would be this, and this would be the recursive form. Notice that both of these definitions give rise to the same actual list of numbers, the same numbers in the same order, but one way of doing this is closed and the other way of doing it is recursive. So now let's define a couple of special types of sequences. So an arithmetic progression is, or I guess I should say can be written as a sub n equals d. Do I want to write it like this? I think I'm going to write this a different way. A plus dn. Alright, so what we're doing is at each stage n, we're adding the same difference again and again and again. We could also define it, or a sub, let's define this one with a sub 0. A sub 0 equals a sub n equals a sub n minus 1 plus d. So we'll notice that we're just adding d each time. Let's do an example of this. Let's define, so again, this is the closed form definition, and this would be the recursive definition. So let's define, let's do about 7, 10, 13, 16, dot, dot, dot. So hopefully you can see this pattern. It's going to be 7 plus 3n. Okay. Could also write this as a sub 0 equals 7, and a sub n equals a sub n minus 1 plus 3. All right. Now similarly, but different, a geometric progression can be written as a sub n equals a times r to the n. So this was adding a number each time. This is multiplying by a number each time. Or we could write it as a sub 0 equals a, and then a sub n equals a sub n minus 1 times r. So an example of a geometric progression would be something like, let's do 3, 6, 12, 24, etc. And this is going to be 3 times 2 to the n. So this is an example of a geometric progression. Now another popular recursive sequence is the following. A sub 1 equals a sub 0 equals 1, and a sub n equals a sub n minus 1 plus a sub n minus 2. And if you want to, pause the video and take a sip of water. Try to work out what this sequence is. The sequence is going to be 1, 1, 2, 3, 5, 8, 13, etc. And this is the very popular Fibonacci sequence. And I remember hearing about this in, like, I don't know, just like activities on the back of a cereal box kind of level, you know, fun math stuff. I remember seeing it sort of not in a serious way and thinking, well, that's okay, so somebody came up with some easy rules to generate a long list of numbers, but I didn't realize that it's actually very important in mathematics. So this sequence of numbers has some really special properties, and I'll just tell you one of my favorite ones. You know, is that if you look at the spirals on a sunflower, so if you look at the way that the seeds are distributed on a sunflower, and you know you have this network of spirals. Well, if you have some number of spirals that are counterclockwise, then you're going to have another number of spirals that are clockwise, and both of those numbers will be Fibonacci sequence, consecutive numbers in a Fibonacci sequence. Most of the time, not all the time, and I don't even know if I drew the right number of spirals here, but that's kind of the idea. Also, of course, the Fibonacci sequence arises in in the tool song lateralis, which is really important. Okay, last thing I want to do is talk about sigma sum. So if I write the sum as I goes from 1 to 3 of f of I, this means f of 1 plus f of 2 plus f of 3. I want you to think of this like a for loop. So for I goes from 1 up to 3, sum up all of these functions that depend on I. So let's do a relatively straightforward example. Let's do the sum as, let's say, j goes from 1 to 3 of j squared. So this is a function of that index. So then when j equals 1, I've got 1 squared. When j equals 2, I've got 2 squared. And when j equals 3, I've got 3 squared. So this is 1 plus 4 plus 9, which is 14. And you might say, well, how do I know to add? If I'm just generating all these numbers, how do I know to add? And that's because this is the Greek letter sigma, which stands for sum. Those of you that have had calculus, you might have noticed that an integral sign kind of looks like an S, and that's because, wow, those do not look like S's. And that's because it's an S for sum. It's a Riemann sum. So this is a different kind of sum. This is a discrete sum. Where in discrete math, we're going to do a discrete sum as opposed to a quote-unquote continuous sum, like the integral that maybe you've seen before. And if you don't know what an integral is, don't worry about it. Now, we can also do sums of sums, and this is kind of the main thing that I want to finish with. So if I have the sum as I goes from 1 to 3 of the sum as j goes from, let's say, 2 to 4, let's do 2j minus I, then what I can do is I can just evaluate this inner sum first. And so this is going to be, well, the outer sum as I goes from 1 to 3 of what? Well, I first evaluate this thing when j equals, I first evaluate this thing when j equals 2. So I've got 2 times 2 minus I. Then I add to this thing when j equals 3. So 2 times 3 minus I, plus then I evaluate this thing again when j equals 4. 2 times 4 minus I. And this becomes the sum as I goes from 1 to 3 of what? Well, it's 4 plus 6 plus 8. 4 plus 6 plus 8 is 18. Minus I, minus I, minus I, so 18 minus 3i. And now I've got, just like the sum before, I've got a function in a single index. So this is going to be 18 minus 3 times 1 plus 18 minus 3 times 2 plus 18 minus 3 times 3. And so this is, well, 18 plus 18 plus 18 is 54, minus 3 minus 6 minus 9, so 54 minus 18 is equal to, oh goodness, 36 it looks like. 36, and that's our final answer. Anyway, you might want to rewatch this, look up double sums or summation notation. And rewatch this last little exercise example.